প্রথমেই আছে নির্মলেন্দু বিশ্বাস। টাইম হয়েছে না হয়নি, এখন 2 মিনিট বাকি আছে। মিক্সচারটা অফ করে রাখো। হ্যাঁ, afternoon, sir.
Yeah, good afternoon.
Yes. So we have total 6 papers.
Oh, yes.
Okay. So we'll start at 1:30 correctly. Okay, sir.
I'm ready.
Okay,
I hope
sir.
they are also. Okay.
Okay, sir. Okay, sir. So we'll welcome Dr. Sanchay Mukherjee
Thank you.
as our session judge, and Professor Madhav Mondal also here, and I will coordinate it. So we have 6 papers: TF 1578, 1586, and 1588. So the first is 1577, 1577. Professor Nirmolendu Vishwas.
Yes, good afternoon.
Yes.
Good afternoon.
You can start, sir. Thank you.
Okay, thank you. Thank you so much. Very good afternoon to the session chair as well as to the audience. Thank you to the organizer for providing me the opportunity for presenting our work. So I'm going to present our work, MHD thermal convection of nanofluid saturated porous cavity heated linearly. This work actually has been carried out by final year UG student. So right now he's doing his MTech MTech at IIT Kharagpur. So that's why I need to present it. So thank you everyone. Okay. So before going into the detail about the problem on MHD thermal convection, the basic thing, natural convection. Natural convection, that means buoyancy driven convection may happen when there is a temperature gradient. So due to the temperature gradient, buoyancy induced convection can generate. Now when this buoyancy driven convection is considered in the presence of magneto hydrodynamic, that means in the presence of magnetic field, then the convective flow phenomena can be termed as magneto hydrodynamics. So these magneto hydrodynamics can find numerous application, especially from biomedical device, even also various thermal device where precise control is very important. So day by day application of this magneto hydrodynamics are increasing. So we have chosen this area for the study. Although several researchers have conducted different work on this Magneto Hydrodynamics, but still some of the question yet not answered. So that's why we have chosen this area. So from the application point of view, MHD convective transport phenomena can be found in targeted drug delivery system, even also fuel cell application, even also multi-physical scenario. Now, why this Magneto Hydrodynamics has been considered? Day by day, although technological advancement are happening, but designers are facing tremendous challenges due to its miniaturization and also high demand on the performance. So to control all these features, so there are researchers who are devoting themselves for optimizing the performance as well as its sizing can be reduced, so that point are taken care of. So that's why we have chosen a classical problem that is square cavity heated linearly. So we have considered a square cavity filled with nanofluid saturated porous media, and we have taken an atom so that we can check whether Magneto Hydrodynamics can affect its heat transfer performance or not in presence of porous media. So that's why we have conducted this study. So from the geometry, from the description of the geometry point of view, you can see the cavity is the square cavity, and both the vertical walls are heated linearly, but left wall is heated with decreasing features. That means temperature is decreasing with the increasing Y, whereas the right wall temperature is increasing with the increasing Y. So the bottom wall is taken as adiabatic and top wall is taken as cold. That means heat can be transferred through this wall to the surroundings. And the porous media has been modeled considering Brinkman-Forchheimer-Darcy model. So in brief, it can be termed as a BFDM model. So the flow has been taken as a steady, homogeneous, incompressible, and Newtonian flow, and the working fluid has been taken as a nanofluid consisting of host fluid water having Prandtl number 6.93 and micron size nanoparticles, that is copper nanoparticles, and we have modeled the buoyancy term adapting the Buznik approximation. Now these are the governing equation, continuity equation, momentum equations, and energy equation. For obtaining these governing equations in the dimensionless form, we have utilized some of the scaling parameters for the X and Y, and also pressure, and also for temperature, and accordingly we have defined Rayleigh number, Prandtl number, and Hartmann number. This Hartmann number has been utilized to define the magnetic field. Now these are the boundary condition, isothermal temperature at the heating point, and this isothermal temperature is a function of increasing Y. So at the vertical walls, two different temperature boundary condition has been chosen, and for presenting the global parameter of the heat transfer rate, so Nusselt number has been defined. Now in the governing equation, some of the correlations for the nanofluid has been chosen to incorporate the thermophysical properties. From standard literature, we have taken the thermophysical properties of water and copper. We are not going into the detail about this. The whole analysis has been carried out utilizing in-house developed CFD code. This code is basically based on finite volume method, simple algorithm technique, and central differencing scheme has been adopted for diffusion terms, whereas quick third order upwind scheme has been utilized for the advection terms. And convergence level has been chosen in the order of 10 to the minus 7 and 10 to the minus 9 for the residuals and mass defect. And for this study, extensive grid independence study has been carried out, and finally 160 by 160 grid has been chosen. This grid study has not been presented here due to limitation in the pages. Now overall result has been presented utilizing streamline isotherm contour plots, and overall heat transfer parameter utilizing Nusselt number. The range of parameters are Rayleigh number. Two sets of Rayleigh number has been chosen, 10 to the 5 and 10 to the 6, so that convection mechanism can be presented. And Darcy number has been chosen 10 to the minus 5 to 10 to the minus 1, and Hartmann number has been chosen as 0 to 100. Now this Darcy parameter has been taken to present the permeability of the porous media. Now from the result we can see with the variation of the Rayleigh number for the case of base fluid, that is it is not containing any nanoparticles, but nanofluid it contains nanoparticles. We can see the trend of the streamline distribution almost similar, and also for the isotherm the trends are almost similar, but we can see heat transfer parameter it shows some significant changes. Now when we can see the higher Rayleigh number cases, then we can see instead of 2 circulating cells, there appears 2 more circulation cells at the upper portion of the cavity. Now this is happened as left wall is heated linearly. The bottommost point is at highest temperature, whereas at the right wall at the top point maximum temperature may happen. So that's why there are localized cooling section near the top portion of the left wall and on the other side at the bottom side of the right wall. So due to this zigzag localized cooling section, these flow features are forming, and as we can see isotherms are distorted due to this uneven temperature distribution. And for the higher Rayleigh number 10 to the 6, we can see there is a significant difference for the heat transfer parameter. So we can say adopting the nanofluid, heat transfer is enhanced in the order of 10 to 12%. Now when Darcy number of the porous media is increased from 10 to the minus 5 to 10 to the minus 1, we can see strength of the fluid circulation are increasing. As the Darcy number is increasing, so resistance to the flow field is decreasing, so more amount of heat can be transferred from heated wall to cold wall. So that's why strength of the stream function are increasing, and also the heat transfer rate are also increasing. Similarly, the effect of the Hartmann number can be realized from the figure. Basically, the case of no Hartmann, that means 0 H equal to 0 case, has been presented here in the first column to understand how the magnetic field can affect the flow field. From the governing equation, we can understand due to the presence of the magnetic field, there is a negative source term in the y momentum equation. So that's why this negative source term is always counteracting the buoyancy term. So when the magnetic field is increasing, that means Hartmann number is increasing from 0 to 100. The flow field is distorted due to the reduction in the buoyancy force. This effect can be seen from the isotherm distribution also. So whenever a Hartmann number is increasing, heat transfer parameter is also decreasing. It is reflected by the average Nusselt number. Now with the increasing rate of nanoparticle concentration, we can see that there is no significant changes in the flow structure, but heat transfer characteristic is increasing substantially. We can say from 0.001, that means 0.1% to 5% enhancement of the nanoparticle concentration. Heat transfer rate is increasing from 5.3 to 6.06. So it is substantially increment. So from the heat transfer characteristic curve, we can clearly see that with the increasing in the nanoparticle concentration, heat transfer rate increasing monotonically, and this increasing trend are following for the both Rayleigh 5 and Rayleigh 6. And also we have analyzed the other heat transfer characteristic for the varying Darcy number and also Rayleigh number, but we have not presented here. now from this analysis we can understand that as the Rayleigh number increases, the strength of the flow vortices are increasing, and also it helps to improve the heat transfer rate. And as the permeability of the porous media is increasing, so resistance to the flow field is decreasing, so heat transfer rate is also decreasing. With the inclusion of the nanoparticle, heat transfer rate is increasing substantially. But in the presence of the Darcy medium, this in the presence of Darcy medium as well as in presence of the magnetic field, this heat transfer rate is decreasing, keeping other parameter fixed. When magnetic field is increasing, heat transfer rate substantially decreases. Finally, the effect of heat transfer on the effect of heat transfer with the increasing nanoparticle concentration shows a significant improvement. So with this temperature condition, we can realize that impact of Hartmann number as well as Darcy number have a significant role on the heat transfer performance. So outcome of this study could be helpful for designing new device, and it will be very helpful for the designer. So some of the references are presented here, and thank you for listening.
So, okay, nice presentation. Thank you. So, is there any question from the audience? We can take one or two questions.
I think no questions. So I have a question. Sir, can you explain, can you verify or explain how the porous cavity properties will affect this experiment or these explanations? Porous cavity property.
Porous cavity property. Actually, for this analysis, so we have fixed the porosity, but we have changes its permeability. That means Darcy media effect has been varied only. But if we consider the effect of the pores of the porous media, that means porosity, then heat transfer can be different. So that part we have not presented in this paper, but we have analyzed this feature also.
Okay. And is there any difference in if the saturation conditions differs?
Saturation conditions, that means?
The saturation temperature, pressures, those properties, if varied, then how the explanations varied?
Oh, actually, our analysis has been limited within the laminar zone, and also the temperature range has been taken in such a manner so that the dimensionless temperature is not so high, and our Rayleigh number is limited to 10⁶ only. So that's why this temperature effect have no significant role in this present study.
Okay, can you give some examples? Already these explanations or this type of research has been worked in real field?
You can see the application of the fuel cell is now increasing day by day. So there are several studies are going on with this application. So fuel cell, you know very well, there are pores are there. So gas is flowing through one side, and chemical electron exchange are happening there. So this fuel cell control is very important, and collection of water is also another part. So our analysis could be adopted for this kind of application. Even also for extracting the oil from the underground system, there are various complexity are there. So this is also a porous body, and with the help of magnetic field, we can control this field.
Okay, there are several nanofluids are there. This is specified for particular case or for any nanofluid like?
No, we have chosen copper water nanofluid.
Okay. Thank you, sir. Thank you very much. Thank you, sir. Sanchan sir, please.
Actually, I have a small query. Right. So, is there any plan to validate your result with some published work or some experimental observations?
Thank you, sir, for your question. Actually, we have already conducted extensive validation study, and also
Okay.
we have published our work in international journal. So,
Okay.
from that point of view, we have also checked our code considering theoretical properties of the nanofluid. Even also, we have checked with the experimental data. So, it is closely matching with the experimental data. So, our code is quite capable to handle these flow features.
That means the experimental data, the experiment was done by some other researchers, no?
Right, right, sir.
Okay, okay.
Our planning to conduct experimental work in coming future, so we are planning for that.
And you have plotted the results with the help of any software like ANSYS or MATLAB like
No,
that?
actually we have written code using Fortran, and
Oh, okay, okay.
from the source
Got
data
it.
we have draw the streamline isotherm through take plot and origin plot.
Okay, okay. Okay, okay. Got it. Thank you. Thank you.
Thank you.
Thank you, sir. Next would be TF1578.
Yes,
Mr. Shayan Banerjee.
yes, sir.
Yes. Please start your presentation. Thank you.
Yes. Yes, sir, my screen visible?
Yes, yes. Very much.
Yes. Thank you, sir. Thank
Please
you,
go
sir.
ahead.
Good noon, everyone. So my topic is mixed convection condensation of vapor with non-condensable gas over a vertical flat plate with the help of ODE-based integral solutions. So here is my contents. So what is condensation process? Condensation process is a phase change process from vapor to liquid at constant temperature. So during condensation, when phase change occurs, mainly since from vapor to liquid, mainly latent heat is removed, not sensible heat. So this condensation process is used in many system and process such as cryogenic and refrigeration systems, air conditioning systems, also in distillation process in chemical plants, in evaporator systems, or in nuclear power plants, especially in safety measurement systems. So in nuclear power plant, there are lots of water cooled nuclear reactors such as boiling water reactor, pressurized water reactor, where LOCS, that is loss of coolant accident, appears as one of the main accidental scenario. So during this situation, actually due to less water circulation, water vapor is released at very high temperature and high pressure. So this water vapor over pressurized the contaminant and then threaten the integrity of the contaminant seriously. So in this situation, actually water vapor is required to condense very rapidly to maintain the reasonable pressure, and so PCCS, that is passive contaminant cooling system, contaminated water spray systems are the such systems that provide rapid condensation during this situation. So condensation process is very much required in nuclear power plant in safety measurement systems. So our objective is to investigate the effects of non-condensable gas for laminar film condensation over vertical flat plate, because we know that in every practical situation, steam always contains some amount of non-condensable gas. This non-condensable gases may be air, helium, etc. So these non-condensable gases have very poor thermal conductivity and non-diffusive nature. So it continuously accumulates as liquid vapor interface during the process, and so reduce the condensation heat transfer rate due to its poor thermal conductivity. So researchers have found that when only 1% of air by mass is present, then heat transfer coefficient of steam can be reduced by 50%. So it is our objective to study the how it affects the heat transfer process or condensation process, the presence of non-condensable gas. So here is our model. So this is vertical wall or vertical plate which is maintained at wall temperature TW. So here is free steam is at U infinity, T infinity, P infinity, W infinity. U infinity is the free steam velocity, T infinity is the free steam temperature, P infinity is 50 pressure, and W infinity is the fraction of non-controversial gas in the external flow 15. So TW is get maintained low than the T infinity. So condensation process is occurring. Near the wall, a thin liquid film is we can show a thin liquid film of thickness delta L. Behind this mixture layer is generating. So we divided this mixture layer into three parts. That is mixture layer, mixture momentum layer or thickness delta M, then mixture thermal layer or thickness delta T, and mixture concentration layer or thickness delta W. We did not divide the liquid layer because the thickness of liquid layer is very small. So we did not divide the liquid layer. Rather, we divide the mixture layer in three parts. So here is our assumption and some simplification. That is, we consider isothermal plate, which is vertical and smooth. Also, steady state incompressible flow is assumed, and laminar flow in both liquid and mixture layer is considered. No slip condition between plate and liquid film. Also, liquid and mixture layer between liquid and mixture layer is considered. And film interface is impermeable for non-conventional gas. Also, homogeneous mixture of water vapor and air is considered in our study, and we do some property average, and also potential flow is assumed outside the mixture layer, and boundary approximation is very much valid. That is, all the thickness delta L, delta M is very much less than the length of plate. Also, gravity is considered as only body force term. So we do some property average in this way because we consider homogeneous mixture of air vapor mixture. So we know that in case of two-phase systems, property average we require. So we apply Mercator's relationship in our study for weightage average property, and the mixture properties are we define at arithmetic mean of free steam temperature and Walton temperature. So here is our formula. So epsilon is the property, any property. It can be density, it can be anything. So epsilon M is the mixture property, epsilon NC is the non-conventional gas species property, and epsilon V is the property of vapor, and WNC is the mass fraction of non-conventional gas in free steam or non-conventional species. Yes. So here is our governing equation. So there for liquid layer, this continuity we define this continuity equation, momentum conservation equation, and energy conservation equation. For mixture layer, continuity equation is this, and momentum conservation equation is valid from delta L to delta L plus delta M. That is in the mixture momentum layer. So and energy conservation equation is valid from delta L to delta L plus delta T. That is in the thermal layer. So this is energy conservation equation, and this is species gas concentration conservation equation from delta L to delta L plus delta W. This is and also this is the we know that total mass fraction is 1. That is mass fraction of non-conventional gas and vapor. So from this we can define only one species concentration equation. Then we can from this equation 8 we can also define conservation equation of vapor also. So here is our boundary conditions. This is slip condition, no slip condition. At the wall, velocity is 0. At the interface, there is interface velocity defined as EY, and this is free stream velocity U infinity. This is wall temperature at y equal to 0. This is interface temperature Ti. This is interface temperature. This is free stream temperature. This is interface concentration mass fraction Wi, and this is W infinity as the free stream. So here is our interfacial conditions. We define interfacial mass balance equation, interfacial shear balance equation, and this is interfacial energy balance equation. So interface non-conventional species concentration balance is written in this way, and interface temperature you can calculate it from Clapeyron equation, and also interface concentration Wi we can calculate it with the help of this equation 9n, this equation, last equation. So these are all PD equations, partial differential equations. Then we converted them into liquid layer integral equations from PD to integral equation. With this in this way we write. So also this is for micellar momentum conservation, micellar energy conservation, micellar concentration conservation. And then we assume some suitable profile. This is liquid layer velocity profile, that is cubic profile, with the help of also boundary conditions. And this is liquid layer temperature profile. This is quadratic profile. Mixture layer velocity profile. This is also quadratic profile, we assume. This is mixture layer temperature profile, and this is mixture layer concentration profile. All are this quadratic profile we assume. Only velocity profile is we assume cubic, because thickness of the liquid layer is so small. So otherwise it can be a linear profile will be. So we assume cubic profile. So these are our some non-dimensional parameters we consider, and these are some non-dimensional numbers we apply in our study. So Reynolds number for L is for liquid layer, M for mixture layer. So this is Reynolds number for liquid layer. So this is Reynolds number for mixture layer. In this Prandtl number, Peclet number, Jacob number, and Gaston number we apply in our study. So we have 1, 2, 3, 4, 4 variables delta L bar. All these are in non-dimensional parameter. Delta L bar, delta M bar, delta T bar, delta W bar, and PIWI interface, temperature interface, gas concentration, mass fraction. And we in our profile assumptions there are some variable, that is B1 and C2 we can see in liquid layer velocity profile and liquid layer temperature profile. We also consider these are all function of X. So we have 8 variables. So we need 8 ODE equations. So we put this profile, velocity profile, temperature profile, all of this in the linear equations. So in this way we generate 8 ODE equations. We form 8 ODE equations. These are ODE1 derived from the liquid layer continuity equation. In this way, ODE2, ODE3, ODE4, ODE5, ODE6, ODE7, ODE8. We form 8 ODE equations, and we solve them in MATLAB ODE solver ODE23TV. Here is some parameters we use in our study. So for the validation, we extract the results and we calculated Reynolds number, Nusselt number, and Gaston number all for liquid layer, and from that we plot Nusselt number by Reynolds number to the power half versus Gaston number by Reynolds number square. Gaston number by Reynolds number square is Richardson number, which is also not dimensional number. So we compared our results with mathematical model of Liu et al. And experimental works of Jacobs. So this is figure 1 is the comparison with experimental data of Jacobs. So here Gaston by Reynolds number square, that is Richardson number is in the range of 10 to the -1 to 10 to the power 0 approximately, that is 1. So this is in the for forced convection region. Because we know that when Richardson number is very less than 1, so this is forced convection region, so it is approximately in forced convection region. And also figure 2 is the comparison with numerical work for Liu et al. So here also it is in the forced convection region. So we compared our results in this way, and this is velocity profile. So the red color is mixture velocity profile, and also okay. So this is blue color is liquid velocity profile. It is appear as linear profile, but actually this is because of the very thin thickness of the very small little thickness of the liquid layer. So it is actually appearing as linear profile, but it is not. And this is mixture velocity profile. So this is liquid temperature profile, and also this is mixture temperature profile, and this is liquid temperature profile. So this is at interface. So at the wall it is TW that we maintain, and also this is achieving the feasting temperature at the interplate. So this is concentration profile. So in the liquid layer there is no concentration profile, it is only mixture layer. So it ends at this point. So this is interface temperature, interface concentration profile. So as we know that non-conventional gas continuously accumulates as the liquid vapor interface. So it continuously the concentration that is mass fraction of non-conventional gas continuously increasing. So we can see a increasing profile. So as the mass fraction of non-conventional gas or in our study air, the concentration of air continuously increasing, then also concentration of vapor will continuously decreasing. So partial pressure of vapor will be continuously decreasing, and so will be continuously decreasing, and then the temperature will be continuously decreasing. So when the interface temperature continuously decreasing, then our driving force for temperature, driving force for condensation process, that is the temperature difference, will be continuously decreasing. That is why it affects the condensation process. So we can see that when we vary our non-conventional gas mass fraction from 0.01 to 0.5, it continuously decreasing in this way. So it continuously affecting the condensation process, the increasing of non-conventional gas. So our summary is that heat transfer rate and rate of condensation is decreased with increase of air mass fraction. Also velocities and temperature profiles for both and liquid mixture layers, for both liquid and mixture layer follows the boundary layer distribution. So velocity profile is linear in liquid layer due to small thickness, but in mixture layer it is non-linear in nature. So due to impermeable nature, non-conventional gas continuously accumulates at liquid vapor interface, and it affects the condensation process, and also the mass fraction increases continuously along the axial direction of isothermal plate, and interface temperature continuously decreasing along the isothermal plate. So here are some references we directly use in our study, from which we take help. Thank you.
Thank you. So I leave it to the audience again. Is there any question?
Yes, sir. Sir, I have one question.
Yes, please carry.
Yes.
So, Mr. Sayan,
Yes, sir.
how you have tracked the interface? By which
So,
method you have used?
We apply interfacial conditions, some interfacial mass balance, interfacial shear balance.
In a cell, suppose. So
Yes,
in
sir.
a
Yes.
so in a cell, suppose you have so in the interface there will be one cell will be partially filled with fluid and both the liquid and gas. So to find out the density of that cell in that cell, how you have which method you have used?
Actually, this is our analytical model, and not it is computational model, CMT model. So
Okay.
yes, this is our analytical model.
Okay. Thank you.
Yes, sir.
Any
Sanchal
question?
sir.
Okay.
I have one query.
Yeah, please.
Yes.
Actually, Shayan,
Yes, sir.
the thing is that you have divided the mixture layer into three segments,
Yes.
but not the liquid layer. Is it
Yes.
only due to the thickness, small thickness of the liquid layer, or is it something else?
Yes, small thickness of the liquid layer.
Okay. And for the interface, you have used the assumed profiles that you have shown, and is the profiles that you have collected from is there the profiles are from some literature? Have you
No,
found
no, no,
it?
no, 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 no. First, we assume UL by EY, that is in the form of non-dimensional. So UL by EY is equal to A1 plus B1 eta plus C1 eta
Okay,
square plus D1 eta cube. Then
and
we
then you have used the
add
boundary condition to find
boundary
out the.
conditions. Yes,
Yeah,
yes,
yeah.
yes, yes,
Okay,
yes,
okay, okay, okay. Got it. Thanks,
yes,
thanks.
yes.
Okay, thanks. So I have one small observation. It is
Yes.
not a question actually. I think whenever the graphs are presented,
Yes.
you have rightly pointed out the previous research work and validated with them, like Liao, Italy, or
Jacob's
something,
experiment.
Jacobs. And
Yes.
as my humble suggestion is that please provide the year of publication also within parentheses.
Oh,
That
oh,
will help. Sometimes same author publishes
oh,
several.
oh, oh. Actually we defined it in the reference part. Okay, I will.
Within parentheses, if you
Yes.
just write 1966 or like that, that will
Okay.
help
Yes.
at a glance. Okay.
Thank you.
And also, you have rightly, very laboriously have done the work. The only thing is that, particularly, how would you use your work in reality? That means you have done the work for a particular, say you have assumed some profile and did all the things and validate, okay, but how would you use your result in real life? Suppose you have given the graph to somebody, would he or she use the work readily, or what is your suggestion?
Yes, in reality, actually, we assume lots of assumption, and this is one type of analytical work. So, in reality, this may be directly applied because in our work, we assume plate length that is very small, that is in the range of 10 to the minus 3 to 10 to the minus 2. So it cannot be in reality plate length that is in meter 10 to the minus 3 to 10 to the minus 2 meter. It in reality it cannot be so small length of plate. So there is some lots of difficulty directly using.
Also, what I feel that since it is a vertical plate, isn't it?
Yes.
So
Yes.
it is very difficult to ensure that the small thickness of the liquid layer would be entirely filled up with liquid.
Yes. Sir. Yes.
Understand what I want to mean?
Yes. Yes.
Since it is a vertical plate, it is very difficult to ensure that it is completely filled with liquid only. So
Yes.
that is also, I think, one problem.
Yes.
So that may be your future scope. If you want, you can further go ahead with it. With some more modifications and development improvements. Okay.
Yes. Sir.
So thank you. If there is any question, or otherwise we can go ahead.
Okay,
Dr. Kundu.
No, sir. I don't think anyone is more there. Okay.
Okay.
Thank you.
Thank you.
Thank you, sir.
The next would be 1580. Is there anyone? 1580. No. Next, 1581. Is there anyone? 1581. No. Next, 1586. Is there anyone? 1586. Uttam Roy. No, I don't think so. Okay, the last one is 1588. Abid Das.
Yes, sir. Yes, sir.
Yeah, okay. Just prepare and start.
Sir, I have to share the screen now.
Yes.
Okay, sir. Okay, sir. Thank you.
Thank you.
Sir, can you see the screen?
It's clear.
Okay, sir. Good afternoon to all of the teachers.
Afternoon.
So here I am going to present my paper on liquid desiccant dehumidification. So my paper title is The Performance Evaluation of LICL and CaCl2 based falling film dehumidifier with surface modification. So my co-authors are Rajat Subra Das and Kaushik Das. So these are my outlines. First, I will be describing what are the needs of liquid desiccant system, and then I will give an overview of what are the difference between the conventional vapor compression system and the liquid desiccant system. Then I will give some introduction about the how the falling film contactor works in liquid desiccant dehumidification system. Then I will give the validation of my work, then the results and bibliography. So in general, we spend most of the time at our home. So the energy consumed to maintain the environment, specifically the temperature and humidity for the room, is almost 41% is primary energy, and 50% of that is consumed by the air conditioning and the ventilation heating system alone. Also, the refrigerant used in the conventional vapor compression system are hazardous to the environment and the ozone layer. So first we have banned the CFCs and HCFCs in the Montreal Protocol in 1987. Now what we are using presently, R134A, is also 1430 times global warming potential, that is GWP, of that of CO2. So it is also very harmful. Then this liquid desiccant dehumidifier can be a potential alternative to the conventional air conditioning system. Now from this graph you can see, let me zoom it on. So from the graph you can see, if we use the conventional air conditioning system, if this part is our outdoor air, then first the outdoor air has to be cooled up to the saturation line, then the required moisture will be removed, then it has to reheat back to the room temperature. So there is a lot of energy is wasted. So we prefer when you use the liquid desiccant system, it does not require the especially electricity or the fossil fuels. We can use any waste heat or the low grade energy like solar energy to drive the system. Also here the heating and sensible and latent load are decoupled, means we can separately cold and dehumidify separately. The property of liquid desiccant is hygroscopic in nature, means it absorbs moisture. The liquid desiccant are basically salt, so they tend to absorb moisture from air. So we use that property of the material to dehumidify the air. Now, a falling film contactor is just a vertical plate or the vertical channel from where through the wall the liquid desiccant will be flown down under the action of gravity, and the other side the air will be flown counter to the solution. While flowing counter to the air and liquid desiccant, the liquid desiccant absorb the moisture and get diluted. Then the diluted liquid desiccant is again sent to the regenerator, where it is heated and the rejuvenation is done there. So again we make it to the concentrated for the inlet. Now, one main advantage of this is that this falling film contactor has very high surface area to volume ratio. which helps in the interaction of liquid and gas. These are the some of the important literature review that is being done here. Grossman, he studied the fully developed laminar flow in a inclined plate. Then Banerjee et al., he did two-phase model with some user-defined function in ANSYS fluent. Then same type of work is done by the Lue et al., where he extend his work and he developed some more robust formulation to solve the problem. Then again, Lue et al. Did internal cooling, where the water will be flown to maintain the temperature of the liquid wall. Then Wen et al. Developed a quasi 3D model where he has considered the shrinkage factor to give a very realistic condition to the numerical model. Gaps in the literature. Now, while the desiccant absorb the moisture, so at every instant, the property of the liquid desiccant will change. But most of the earlier work, they have not considered the change in property, because in numerical model, it is very tough to use. Then most of them use the steady state nature, but in the problem itself is very transient in nature. So it also given approximation result. Then wavy nature of the liquid desiccant also they have neglected. Means they have considered the film thickness of the solution is constant, which is completely unrealistic, because when the solution will flow, then it will try to spread throughout the surface. So the thickness and the waviness of the solution is also considered in this work. Now, these are the physical model I have. So here you can see that this wall has this liquid desiccant is falling through this wall, and from this side the air will come inside the dehumidifier. Now the air will be having higher temperature than that of the liquid desiccant. So we know that the vapor pressure is a function of temperature. So the vapor pressure of water molecules in the air will be higher than that of liquid desiccant. So the moisture will get driven by the this vapor pressure, and it will fuse in the solution. When it fuses in the solution, it releases the sorption energy and also the energy due to phase change. So there will be a exothermic reaction will be going on there. So it is also considered in this paper. Now the meshing is done so that the most of the critical physics is taking place near the interface. So we have meshed the near wall interface is very finely meshed. Then we have changed the model to a wavy surface. The equation of this is x is equal to a sine 2 pi by lambda y. So where lambda is the wavelength and the a is the amplitude. This equation is taken from the literature. Then the meshing method here used is also the same way. Near the wall, the mesh is very finely created. The boundary condition. The velocity of air is kept 0.2. The humidity is 20 gram per kg. This humidity is the specific humidity. Then the temperature is 303. That is 30 degree. Whereas the solution velocity is kept 0.07 to maintain a constant film throughout the surface, because if we reduce the velocity of the solution at the inlet, then the film breakage will take place in some places. The LiCl and Cl2 are the most commonly used liquid desiccant, and we have taken 30% concentration of the both. The temperature is taken around room temperature, that is 25 degree, and the wall temperature is also kept constant at 298 Kelvin, that is 25 degree. These are the governing equation. Basically, this problem needs four governing equation. First one is the mass conservation, then the momentum, then the energy, then the species transport. Now, to track down the interface, volume of fluid method is used, where the density and the viscosity of each cell is calculated by the these two relation 5 and 6 number equation. Then this calculated alpha, that is the volume fraction, is solved by this 7th equation, and the interface will be tracked. Wherever the volume fraction is in fraction, where the alpha is in fraction, the interface will be drawn in that area. The volume fraction is gas is achieved by alpha G plus alpha L. Now, the interface condition. Now, when the solution absorbs the moisture, the driving force of that is the equation number 9, where the equilibrium humidity is defined by the vapor pressure of the solution, and we know the inlet air humidity. These equations are put in a UDF and is written in C program. Then it is hooked in Fluent. This is the ANSYS Fluent solver to customize our problem. These are the local mass transfer coefficient, and the surface velocity of the liquid film can be found out by U surface is equal to this 1.5 QB into 3 mu by QB by rho G. Here I have explained how the equilibrium humidity of the solution is calculated. The energy source, so as I have told that when the water molecule fuse in the solution, it will release the latent heat. So that latent heat is given by the energy source term. Now, how the UDF works? First, the fluent will take the cell variable like density at that point, then it will give to the UDF. Then UDF will calculate the updated values. Then it is again sent to the fluent. So in that way, like density, viscosity, thermal conductivity, specific heat, mass transfer source, energy source, all these things are being written in user-defined function and is updated in a time basis. Now, here we have done a 2D transient conjugate heat and mass transfer problem, where finite volume is used to solve the governing equation. Then volume of fluid is used to track down the liquid gas interface. The time size is kept around 10 power minus 5 to get a stable solution. The liquid desiccant, LiCl and CaCl2 is used to run the program. Validation. The validation is done with the experimental work of Tao et al. 2019. So since we have done the 2D analysis and we have not considered the shrinkage factor, like when the solution flows through a wall, it tries to shrink. That shrinkage is not considered here. So our result shows 10.31% deviation at max and at the lower end it is showing 4.25. The parameter is outlet humidity selected for the validation. Now to make our model more robust, we have compared the time basis comparison of our present model with the Luo et al. Of 2014, where we have seen each and every step is matched with the Luo's work. How the film flows with the time, that also being matched with the Luo's work, and it gives a very good good matching with the literature work. Results. So here we have compared the CaCl2 and LiCl for the both flat and the wavy case. So here we have found that the LiCl gives gives at 22 for CaCl2 and 34% for LiCl, with the increase of 7% in the surface area. When we have taken the wavy surface, we have kept the overall area in the channel as fixed, but the surface area is increased by 7% for the wavy case. So here we have found that the combination LiCl with the wavy surface perform better. Now, to further understand the physics of that, we have analyzed the mass fraction gradient at the midpoint of the channel. So we have varied the across the x direction how the dehumidification or the mass fraction gradient is varied. We have checked that. There we have found that the wavy profile of the surface increases the film thickness by 21.7% and 12% for LiCl and CaCl2 respectively. Now, so here you can see from the graph that up to a distance of 4.65 for LiCl, 4.64 for CaCl2, 5.6 for LiCl, and 5.2 mm for CaCl2, the film this maintain an uniform mass fraction gradient of 2 m power minus 2 per meter. This is 2 per meter. Means we can say from here that by this way we can calculate the film thickness throughout the plate. This we have done next slide. So here we have taken the same method to track down the film thickness variation throughout the domain, how it is being changed with the time. So here sir, you can see the film thickness of the LiCl is higher than that of CaCl2 for both flat and the wavy case. It is solely because of the reason that the LiCl is much denser fluid than that of CaCl2. That we have taken from the Conde paper. There we have found that the LiCl is having more density and viscosity than that of CaCl2. The wavy surface enhances the film thickness by 15.25% for LiCl and 13.38% for CaCl2 compared to the flat wall surface. Now, the temperature is a very important part in a dehumidification, liquid desiccant dehumidification system. So here we have found that CaCl2 performs better in terms of cooling. Means the CaCl2 reduces the outlet air temperature by 1 degree, whereas the LiCl could not able to reduce that temperature. This is solely because of the higher conductivity of the CaCl2. The whole process is can be visualized from this psychometric chart, where you can see the lines are given in the legends. Now we have tried to analyze what will be the effect of solution velocity on the dehumidification effect. So here we have seen that the solution velocity does not affect the dehumidification. It is because I think that when we increase the solution velocity, the fresh amount of fluid with higher concentration comes in contact with the air, but the air get very less time, that is a less contact time to transfer the moisture to the solution. These two actions counterbalance each other, so we get the very less change in the results with the change in the solution velocity. So in the conclusion, I want to say that the numerical solver is validated with 10.31% deviation with the experimental data. The LiCl solution gives better moisture removal capacity. The dehumidifier with LiCl solution and flat wall gives 26%, whereas the wavy wall and LiCl solution, it can remove moisture up to 44.85%. The CaCl2 solution in both the flat and the wavy wall can be able to remove up to 13.5 to 30% moisture respectively. From here we can say that wavy wall in combination with the LiCl gives the better results. The CaCl2 is found to be more effect on cooling of the air than LiCl. The effect of solution velocity is found negligible in this work. So here is the bibliography. Thank you, sir.
Okay, thank you. So is there any question from the audience? So if any.
Yes, sir.
You can ask any question.
Okay,
Sanjay, sir.
I have some question regarding the applicability of your work. It's a rigorous work, I suppose. Thanks for that. So my question is vis-a-vis with practical air conditioning plants based on vapor compression system. So first question is, what about the efficiency of the system, desiccant cooling system, compared to the conventional air conditioning plant? And also, I suppose this is less costly maybe, but
yes,
what
sir,
is
it is very less costly.
But what is the efficiency? Have you measured the efficiency?
No, sir. The efficiency in comparison to the VCS is not measured, but since the liquid desiccant system is only energy is used to pump the fluid throughout the circuit, then it is used to heat up the solution for the regeneration purpose to again circulate the diluted to the circuit. So that is can be achieved by solar air heater or the waste heat. So it is very, very less.
Okay. Then comes the second question. So regarding the capacity, that means say in terms of tonnage or dehumidified air quantity. So what is the limit of your work? That means what, by desiccant cooling system, how far do we go?
So actually, till now it is in the developing mode. So all the experimental setups are very, very small.
Yes.
So in this also you can see the geometry is 150 mm height and the 10 mm width. Because if we increase the width the meshing will be moved, and seeing the complexity of the problem, so it will take almost 1 month to get one result. In my case, I get almost nearly 1 week to get one result.
Okay.
So we have not taken it for the large scale till now.
Because after all, you have to commercialize the thing, na? So since the air conditioning plant is running and there is already a conventional system, there is already separate vapor absorption system also. You can use that in many plants. So already the system is existing. Only thing is that you have devised some innovative approach for cooling and dehumidification part.
So actually, they have their
The challenge is to
very
accommodate that in a conventional system.
yes, sir, yes, sir.
Whether it can be applicable in a central air conditioning plant, or it is more or less suitable for application in a particular room, like our cooling appliances or your small split units or package units like that.
Sir, so in our conventional VCS system, the air the dehumidification is done by cooling the air below
Yes,
the dew point temperature.
exactly.
But the dew point temperature is very less than the room temperature. So again,
Yes,
we have to heat it back.
exactly.
So we can use this.
No, we
in a-
don't have to heat it back. Actually, it is taken up by the heat load of the room itself.
Okay. So
Yes, yes.
yes.
You don't
So
have to reheat it.
reheat it.
Reheat is
Okay.
a separate thing. You have it is all taken care of the heat load of the room system. In this case, I don't know how can you cater for that heat load.
Sir,
That is
because
another question.
so in the VCS system, there when you dehumidify the air below the dew point or the dew point temperature, it takes a lot of energy. Suppose you want to reduce 30 degree to 25, so you cannot do that. If you have to do 30 to 18 or 17, then the dehumidification will take place. So we can club these two methods where the liquid desiccant system will be take care the dehumidification part, and the air condition only reduce the suppose 30 to 25 degrees Celsius. So it can
So this system can act as an auxiliary system.
exactly, sir. Yes, exactly.
Okay. Okay.
It can act.
Then it may help. Okay.
Yes, sir. Yes, sir.
Any other question from our learned audience? Professor Mondal is also there, I think.
No, sir, I don't take any questions.
Okay.
You can conclude, sir, now.
Okay. Thank you very
Thank
much.
you, sir. Thank you, sir.
Thank you. Thank you, sir. Thank you very much. Thank you. Thank you,
Okay,
everyone.
thank you, Dr. Kundu.
Thank you, sir. Thank you,
You
sir.
have taken a lot of pains. Okay.
No, sir. Okay, okay. It's our job. Okay. Thank you very much.
So I have to send you something, na?
Okay, okay, sir. You send it to through our ICTMA mail
Okay, okay. I will send it. Okay, thank you.
as soon
Thank
as
you.
possible, because we want to.
Yeah,
please
I am almost ready. I am almost
Okay, okay,
ready. So I will
okay.
immediately I will send it. Okay.
Okay.
Thank you.
We will announce
Thank
the
you.
result at 4 p.m. of validity
Okay.
session.
Okay, thank
sir.
you. Thank you all. Very good.
Thank you, sir.
Session. Okay,
Yes,
thank
yes.
you.
Thank you, everyone. Thank you very much.
And my special thanks to the organizers. Thank you.
Thank you, sir. Thank you.
To give me the opportunity. Thank you very much.
Okay, sir. Thank you very much.